So welcome to lecture 7 of this series. So today we'll start from transformation matrix between coordinate systems. Now if we look at the diagram we're given already, we have unit vectors of the coordinate system E1, E2, E3, right? Yeah. So we can see that E1, it's one coordinate system, or E sub I is one coordinate system. Yeah, and if this coordinate system, maybe an object in that coordinate system is rotated, right? You rotate it to in different, we'll get, and this becomes another coordinate. This becomes another coordinate system, right? It's being rotated. So it's very clear that E sub I and E sub I prime are different. They are different coordinate systems, right? Yeah. Well, there's a way you can rotate one. Let's say you can rotate this E1 to move to become E1, I mean EI prime or E1 prime. You can rotate E2, this one, this vertical, to become E2 prime. You can rotate E3 to move this way too, to become E3 prime, right? Exactly. So basically that happens by the action of the tensor. So to move something from E1 to E1 prime, you need a tensor to rotate that, to make that move, right? If you remember what we've talked about transformation matrix, so we need a tensor called, let's call that Q, which we'll call an orthogonal, this is H, orthogonal tensor. What this tensor does is to rotate. It just rotates but does not change, right? Q, and I. Okay, so EI prime is equal to this orthogonal tensor times an original tensor, I mean a vector. So what has just happened is like a transformation, right? From this, this orthogonal tensor rotates this E1 to become EI. From this diagram, that should be clear. This E1 has become E1 prime, E2 has become E2 prime, E3 has become E3 prime. That's what has just happened, and that's possible by the action of an orthogonal tensor, right? So Q, if you write that in the components of Q is QMI EM. Now I guess you can still remember why if we solve this I, we sum on the m's, right? We get an I remainder, right? And this to give you an I index, because the index on the left should be equal to the index on the right. So if we expand this is EI, right? So it becomes E1 prime goes to Q11 E1 plus Q21 E2 plus Q31 E3. I hope you can still remember how we came about this. If you pick IM, will be, let's say you pick M 1, 2, 3, then you pick I 1, 2, 3. So if you write that all those notations, you get this E1 prime. Similarly for E2 prime, you get Q12 E1 plus Q22 E2 plus Q32, sorry, not 32 E3. Then for E3 prime, you get Q13 E1 plus Q23 E2 plus Q33 E3. Right. So if you have QIM, QJM, right? Well, yeah. So okay. Let me just write that out first. Then Q. This is. Let me use a different color. This is Q, right? This is another Q, right? So if you have one Q, this Q, if you flip it, it becomes MI. If you flip this, it becomes MJ, right? To give you delta IJ. What I've just simply written is trying to say that Q equals to, it's always equals to its transpose, irrespective of the way you try to turn it or so it, because what the rotation tensor does is to simply rotate. It doesn't change, right? It just rotates. It doesn't change vector or any or vector or tensor it operates on. So with that, we understand that Q transpose is equal to Q transpose Q, right? To give us the identity. Basically, what I've just written, these expressions are what you can get here. I hope that makes sense. So if you have Q, let's look at this. Q11 is equal to E1 dot Q E1 equals to E, okay, Q11 is a component equals to E1. Remember what E1 is? E1 is like the original coordinate system. Q dot E1 becomes the rotated coordinate system. This becomes the rotated coordinate. Yeah, the new rotated vector, right? So this becomes E1, no, not I, E1 dot E1 prime. So E1 here remains the E1 here, but this QE1 becomes prime because it's been rotated. If you can remember from our diagram, look at this E1, but when Q acts on it, it becomes this. When Q acts on E2, it becomes this, and E3 becomes this. That's what just happened to that one. I hope this makes sense. All right. So for Q11, yeah, what we just said is equal to E1 dot E1 prime, right? And if you have the dot product of this, we are simply finding the angle between two vectors, right? Right. And usually cos theta. So Qij basically is simply cos EI and EJ, right? Or you can say, or you could still be cos EI EJ prime. You're simply finding the angle between the two vectors when you have the dot products, right? So if you remember Q, this is the matrix itself. Qij are the components of the matrix. Components of the matrix. So if we have, for instance, Q, okay, this we've done for, let me see, for Q11, right? And we got this. Let's write an expression for Q12 is equal to the original coordinate system E1, right? QE2. If you look at this closely, this is, let's say Qij is equals to is equal to EI dot QEJ. That's what we are writing out here, basically. So I want this to be on top. And this is equal to E1 QE2 will give you E2 prime because E2 has now Q has acted on E1 to change, is rotated that, right? So this is like simply the angle between, let's assume, okay, let's assume this is E1 and this is E2 prime. So the angle between and the cos of that angle is what is QI2. So in general terms, you can do that for all the 9 values in the matrix. So Q11, Q21, Q31, Q12, Q22, Q32, Q13, Q23, Q33. Right. So this is Q. These are all the terms of Q, right? And if you follow what we've done here, let me use a different color. Follow what we've done, like this example, for what we've done for Qij, right? Q11, Q12, we can get what we can populate the matrix itself. The matrix Q is called is an orthogonal tensor, right? Or it's still, well, it's a matrix because it's 3 by 3, right? or it's still called a transformation matrix. Sorry, my handwriting is a bit poor. I'll write a bit clearly. Transformation matrix. And this transformation matrix between E sub I and E sub I prime. I hope this makes sense, right? Because if you notice, what we've done, we've moved from this point, right? E1 has become E1 prime, and it can only move by the action of a Q, right? So this, what causes that is a transformation matrix. It is Q, right? Does that make sense? So Q is orthogonal tensor transformation matrix, or also Q could still be called the matrix of direction cosines. Well, the cosine of the angle between the vector and its coordinate system is direction cosines, basically. So it's called a matrix of direction cosines. Well, let's look at an example to make things or put things in perspective. So if we have a coordinate system, let's have this E1, E2, or the rotated coordinate system will be in red. E1 prime, E2 prime, right? Okay, yeah. The third one, we are rotating about the third angle. I mean about the third axis, E3. So here is 30 degrees. Here is 30 degrees. Yeah, there's supposed to be a third one, right? But because we are going to be rotating about that, well, let me write that out in explicit terms. So we have E1, right? E1, and we've obtained E1 prime by rotating EI about the E3 axis. So if you notice this diagram, it's only showing, this is for EI, right? You're supposed to have E1, E2, and E3, but we are rotating about E3. So when you rotate about E3, it's about the same point, right? It doesn't, we are rotating about E3. That point, about that axis, rotating about the E3 axis, so that does not show on the diagram because it's still on the same spot. All other points will move relative to that point. So, and because so by rotating about E3, let me just write that down. By rotating about E3 axis, E3 and E3 prime coincide. So it will not show on the diagram, right? Because if that is, let's say it is this here, if it's E3, E3 prime will still fall on this same line, right? So make it E3 prime. Does that make sense? So we have E1, E2, E3, but we are rotating, about E3, E3, and E3 prime will coincide. So what we are supposed to do now is to find the transformation matrix Q. So in clear terms, we have the coordinate system EI, right? But it's being rotated by a Q to give us another coordinate system EI prime this. So now the question is find Q. Right. So I'll be showing you two methods to do this. The first method write it out explicitly. Method 1. Now Q has 3 components, right? Q11. Let's see, do we need to just copy this not to waste time? Okay. So Q has 9 components, right? Q11, 12, 13, up to Q33, right? So because this is Q, we have E1, and we want to find the transformation matrix that moves from that rotates the coordinate system EI to EI prime, right? So to find this Q, now don't forget our diagram. It was we rotated about E3. I mean, rotation was about E3 axis, right? And by that, E3 and E3 prime will coincide, but all other axes we move. E1 moved 30 degrees, E2 moved 30 degrees. How that makes sense, right? So to find Q, to find the components, because the components is what will make up the matrix itself. Q11 cos E1 E1 prime. Now, just in case you are wondering why I'm writing that, if you remember this point here, right? Yes, and how did we get this? If you look at Q11 here, Q11 is equal to E1 dot Q. That's you're going to be multiplying the original coordinate system. Let's say unit vector, and that's E1 dot the rotated, I mean the rotated component, right? Rotated component. That is, we have Q, the transformation matrix times E1 to give E1 dot E1 prime. And when you have this is equal to the angle between E1 and E1 and E1 and E1 prime. So that's why we simply write cos this one, E1 and E1 prime. So that's what you're going to be doing for all the components inside. I hope this is clear. Yeah, so you can just see. So E1, oh sorry, E1, the angle between, I mean, look at E1 and E1 prime, we have 30 degrees in between, right? Yeah, exactly. So for this first question, the angle between E and E1 is simply cos 30, which I believe to be root 3 over 2. It's very simple actually. Just Q11 E1 is the angle between E1 and E1 prime, which is 30, and you find the cos of that. That's same next thing you do for E1 and E1 and E2 prime, E1 and E2 prime. Maybe I should put this diagram so that we can see what we are doing. Okay, E1. The next one will be E1 and E2 prime, E2 prime. The other one again, E1 and E3 prime. Next, go to E2 and so on and so forth. You can pause the video so you can take a look at the diagram, but you get what I'm saying. So basically, what you are just doing is Q11 is simply the original components that you find the angle between the original coordinate system and a rotated one, right? So if you have Q12, I write this pretty fast, but you can slow down the video and try to process what I've done. Cos 120, that's the angle between it. 1 over 2, 1, 3, because E1, E3 prime, cos 90, that should be 0. Okay, now let's look at 2 ones, cos E2, E1 prime, 2, 2, cos E2 prime. The angle between them is cos 30. Q3 2, oh sorry, that should be 2. 2 should be cos E3 E2 prime cos 90 equal to 0. Q3 3 equal to cos E3 prime bracket, that's E3 prime cos 0 should be 1 this time. Okay, so my aim is to make sure you really understand it, right? That all you're doing, if you look at the values at the first place is E1, 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 E2, 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 E3, E3, E3. You're going to be finding the angle between parts of the original coordinate system and a rotated component E1. That would, so 1, 1. If you look at this two, is 1, 1, 1, 2, 1, 2, 1, 3, 1, 3, like that, right? So if you now look at our matrix, you can populate our matrix to have Q is equal to root 3 over 2, 1 over 2, 0, minus 1 over 2, minus, no, that's not a negative, root 3 over 2, 0, 0, 0, 1. And that's the transformation matrix, right? That simply moved EI to EI prime. I trust this makes a lot of sense. Okay. So the next thing we need to do now, okay, yeah, I promise to show another method. This method is pretty straightforward, right? Method 2 is pretty straightforward. So all you need to do is you're going to decompose EI prime into components in the, excuse me, E1, E2, E3 directions, right? So if you look at this very clear, all we need to do is this. We want to find the metrics that change this E1 to become E1 prime, change E2 to become E2 prime, that rotates it. When you rotate it, it moves to this point. What matrix is responsible for that? That's a orthogonal tensor or a rotation matrix or transformation matrix Q. So how do we find the matrix that does that? Now look at, we're going to decompose this E1. If you can remember from your, I call it linear algebra also, or well, not, yeah, I mean for your, for some, I don't know exactly, is it, I think it's algebra, right? To have the vertical component and the horizontal component. So E1, if you try to decompose E1, right, the x component of E1 will be E1 cos 30, right? And the y component of E1 will be E2 sine 30. Does that make sense? E1 cos 30 sine 30. The same thing you're going to be doing for E2. I mean for E2 prime, you're trying to find a vertical axis and horizontal axis for that. E3, remember, we are rotating about E3, so E3 and E3 prime will coincide, right? So E3 will still be itself. Let me quickly go over that again. So to find the matrix that will convert this E1 to E1 prime, this you're going to find the matrix Q that's responsible for that. But this approach, what we do is that this E1 prime, I'm going to find the horizontal component and the vertical component. For E2 prime, we find the horizontal component and the vertical. It could be this direction or this direction. But you only know that by looking at your linear algebra, right? So for E1 prime, no, that's not I. For E1 prime, that will be cos 30 E1 plus sine 30 E2, right, to give you root 3 over 2 EI plus 1 over 2 E2. For E2 prime, will give you minus 1 over 2 E1 plus root 3 over 2 E2, right? E3 prime is the same thing as E3 because when you it was rotated about E3 axis, right? If you look at this if you look at this, it's just algebra in the sense that you are finding E2, the horizontal component of it on the vertical component, horizontal and vertical. But this was rotated about this, so we just have one, we don't have a component. And now if to find the Q from this method is actually simpler if you understand what you're doing, right? So for the E1, look at the E1s clearly. We have an E1 component, E1 component and an E2 component, but not E3 component. The E1 component is root 3 over 2. The E2 component is 1 over 2 root E3 component is 0. For the E2, we have negative 1 over 2 for E1, root 3 over 2 for E2, none for E3. For E3, we have for the E1 nothing, for the E2 nothing, for the E3 1, which is exactly what we have here. But this is a lot shorter, right? Yeah. So you can pause the video and I believe I've tried to explain in both methods what to do. It's good to know both methods, but I guess method 2 will be simpler and shorter as you progress in understanding tensor analysis. So let me briefly talk about transformation laws for Cartesian components of vectors. So transformation laws for Cartesian components of vectors. I'm sorry, my handwriting is it's not particularly the best. So we have a vector that, A is a vector, right? And for this vector, a vector has components. You can have a vector A equals to 1, 2, and 3. Its components are 3, 1, 2, and 3, right? So if A is a vector that belongs, if A belongs to the group of vectors, right? So the components of A with respect to EI, that's talk of components of A with respect to AI is like AI is right is what we use based on what we were talking previously, how to describe A, right? There will be a component in the E1 direction, in the E2 direction, and in the E3 direction, which is like 1, 2, and 3 here, right? So if you have A, we can A equals to A dot EI, and this is with respect to the E1. Similarly, if you want to write, you can have A prime, you want to be A dot E1 prime, which is with respect to the EI prime. So you can have a vector. You can have a single vector, but you can describe that vector with respect to different coordinate systems. Here, with respect to E1 and E1, or EI and EI prime, we have two vectors, right? So two transformations of the vector itself. Also, if you look at this EI prime equals to QMIEM, right? EI prime equals to, well, let me just, I guess this, you're already familiar with this. This is already transformed. This is a transformed coordinate system or a new coordinate system, right? This is a rotation tensor, and this is the original. Yeah, as I've told you before, using M or I, it's all about your own prerogative, but obeying the rules you must obey the rules, but the letters you choose is at your own discretion, right? You have EI here, or yeah, let's see, even if we call this EM, and this becomes EM prime, right? So this is EM, and this becomes EI prime, right? What has done this transformation is a matrix Q, and Q is QMI, which is what we've just written out here. Now we can substitute this this EI prime here, right? So AI prime becomes A dot QMIEM, which is also equal to, you just simply move positions, A dot EM, right? AI prime. So AI prime equals 2. Now, if you remember from, if you look at this 2, if you look at this 2, we are simply multiplying a vector. This is a vector, and this is like the what you used to describe. The axis itself, the different types, right? And this will give us, if you look at this, point here, where is this? It gives you the components, so it will become QMIEM, where AM are the components of the vector, right? No, that's misleading. That's the vector itself. So AM are the components of the vector. Components. So the components. A is the vector itself, right? So, okay. So don't forget A dot EM give you AM. The dot product of the vector itself and what you on the axis, or the coordinate system will give you the components of the vector, right? We can look at it that this is, let me use this diagram already. This is the vector. This is the vector, right? So if this is A times this E1, we describe the components with respect to E1. A times E2 describe the component with respect to E2, and A times E3 describe the component with respect to E3. I hope that makes it clear. So we have this is so this is a rotation or transformation matrix, right? Transformation matrix. These are the original components, and these are the new components now, right? So the new components. Let me write this out in matrix form. Okay, that's not working, right? E1 prime, E2 prime, E3 prime. Don't forget, once you see EI, you can expand up to 3, right? Then Q11, Q12, Q13, Q22, I'm trying to quote corners, Q33, right? Q here, 2, 1, 2, 3, Q31, Q32. Okay. And for the original components, it's going to still remain A1, A2, and A3. Right. Then you can still write in this notation A, that's the matrix notation prime. This is Q. Let's leave the transpose, because that's the way for compatibility's sake, right? So all we've done is we've written A with respect to E1 prime. Right? So you have to make sure this expression, you get to know it. Right. So we've just simply taken this matrix, this one, and we apply this to it to get this. I hope that is clear. Yeah. So just a couple of notes. So the components of the same vector. So you can express one vector with respect. One vector can have different components as a result of the different Cartesian or coordinate system you use, right? Yeah, the system we're using is the Cartesian coordinate system, the unit basis. So the components of the same vector with respect to different, I'll try to write slow and clean, rectangular Cartesian unit basis. So if you have this, let's say for instance, right, and this is a vector A, unit vector E1, E2, E3. So you can express the components of A with respect to this, with respect to E2, and with respect to E3, right? Then if you have a different coordinate system, let's say E1 is rotated to E1 prime, E2 prime, E3 prime. Let's assume you rotate, or even if you go this way, I mean, it doesn't, it's another style, right? You can also express A with respect to this one's E, this one, and this one. A itself does not change, right? But the transform vectors change because A dot E prime is different from A dot E prime this. They are both different expressions. Okay, so A prime is the transformed vector of A. A that this matrix form, right, is the matrix of the vector A with respect to the basis EI prime, right? A, once you have this bracket, we're referring to a matrix there. So it's the matrix of the vector. If you notice, the vector itself does not change, but the basis is different with respect to the basis AI this time, right? Good. So AI prime is transformed A. All that happens, and that transformation takes place through a vector Q, right? So basically, A and A prime are different. I hope that's clear enough to understand. A and A prime are different. Good. So one very vital expression is this. If you have A prime equal to, okay, well, we've written this before basically. Q transpose. In case you're wondering where this is from, if you can see this, what is highlighted in yellow already, you can see that, right? That's exactly what is here. So if you have a vector, an original vector, I like to repeat things for emphasis, and you have a transformation matrix acting on it, you get a transformed vector. This way it sticks to your memory. You get to understand what I'm saying, right? So if you have this, let me just remove this. So if you have this, right? So if you multiply, let's multiply both sides by, write that out, multiply by a matrix Q. Let's multiply both sides by matrix Q, right? So we have Q A prime equals to Q, excuse me, T Q, right? This remains, or I could have put that one in any way, it doesn't matter. This, if you remember, it gives the identity, right? And A to give you A remaining, right? Equals to Q A prime, which is A supersides Q A prime. I hope that's clear. In decal notations, I, right? So this remained Q I M A I A M, right? Vector, I mean matrix, vector, vector. And based on what we've learned before, if you apply, if I mean, so all this trying to tell us that if with the coordinate basis this of, I mean, the components of am prime, I mean, yeah, the components of am prime when acted upon by qim gives ai. Let's look at this. Let's look at this final part, which is an example that will make things very easy. Then we'll close this session. So we have a vector, right? So the components. Let's say we have a vector A. A is a vector, and the components of vector A with respect to E sub I is 2, 0, 0, right? So A, let's say we have 2, 0, 0, 3, right? We can write A this way, A equals 2, because if you look at this, E1, E2, E3, right? We can express, let's say this is A. We can define A in terms of a unit vector from here, unit vector from here, and a unit vector from here, right? Because defining A means what not, I won't say percentage, but what portion of this in addition to this, in addition to this, will give you an A. So let's say A for this. Oh, A, we're already given A already, right? 2E1 plus 0E2 plus 0E3 based on this. That's where we're getting this from. So it means 2, like saying 2 of E1, the E1 is unit vector of 0 of none of E2, but no part from E3. This is what A is. Okay, I hope I didn't make a mistake there. Yeah, that's right. That's right. Okay. So, okay, now let's draw the, so the components of the vector A is this. We already been given the components, but now we are going, the question says find the components of A, but this time with respect to EI prime, right? With respect to EI prime. Now they are not saying that. The question says EI prime is obtained by a 90 degrees clockwise rotation of EI axis about E3, or E3 axis. I like to picture things, draw them out, so put things and make them very clear to understand. E3, E2, E1. This question is quite straightforward, right? So we already have the components of A. We have A as 2E1 plus 0E2 plus 0E3. So A has been defined with respect to the coordinate system E1, EIs. That's E according to EI1, E2, and E3. But now they're saying we should find the components of A, this time with a rotated coordinate system, no longer this one. And they now said this rotation is obtained by a 90 degrees clockwise rotation of EI. 90 degrees clockwise rotation. So E1 clockwise, we're going this, sorry, is it clockwise? Counterclockwise, I think, is what I should write. Okay, I'm sorry about this, but let me write in a different color so you get to know. Counterclockwise, counterclockwise. Clockwise, we're going this way. Counterclockwise, we're going this way, right? Good. So it says, let me use a different color for that. Right, it says EI prime. So we already have EI. We want to, well, we've talked about, we have A with respect to EI. We want A with respect to EI prime. That's what we want. So what we are looking for now is this. So it says E1 rotated counterclockwise by 90 degrees. If you rotate E1 counterclockwise 90 degrees, E1 is going to fall on this, right? So E1 prime. If you rotate E2 here 90 degrees, E2 is going to fall here, E2 prime. right? And if you remember, anytime you are, and if you rotate about an axis, that point does not change, right? So E3 will still be E3 prime. I guess this is quite explicit, so quite easy to understand. Now, so if you look at this very closely, E1, let me use a different color so that you can see the emphasis. So E1 has moved to this position, right? So E1 has now E1 prime. So E1 prime, oh sorry. So E1 prime is now E2, right? That's clear. E2 prime has become negative E1 because this is E2 prime is going, this is negative direction, this is the positive direction. So it's just simply a swap of signs. E3 prime is simply E3 because that is the axis of rotation. So with this we can get the coordinate, we can get the matrix that was responsible for this rotation. And that was kind of very straightforward, right? How do we get that? Now look at this. Q is equal to, let's write E1 prime here, E2 prime here, E3 prime here, right? Good. So to populate this matrix now, E1 prime has no E1 component, no E3 component. So here will be 0, 1, 0. E2 prime has -1 for the E1 component, no E2, no E3. So this becomes -1, no E2, no E3. And for E3, we have E3, so we have 0, 0, 1. And this is the matrix that's responsible for this transformation, right? Good. Now, so that's Q. We have Q, right? Now, we have Q, which is the transformation matrix. We have A, which is the original matrix, right? Or the matrix with respect, not with respect to E. Okay, with respect to EI. Now we still know that we have A prime, which is still the matrix. It's still the original matrix. But this time with respect to EI prime. Now, how do we get AI prime? It's kind of straightforward, is it? So it's simply this AI prime equals to Q transpose A. And I bet if you look upward, you will have seen this formula here, that's here, and also highlighted here. So that's how to get A prime, right? So Q prime, looking at what the Q there, we have 0, 1, 0, minus 1, 0, 0, 0, 0, 1. And A, we already have A as 2, 0, 0. In case you've forgotten where A came from, this is here, right? And that is there. And if you do this correctly, you will have 0 times 2 plus minus 1 plus 0, 0, 0, and minus 1. Yeah, you can cross check what I'm doing. I guess 0, 0 cancel and 0. So this is, so if you look at this now, you have A 2, 0, 0, A prime 0, negative this. So you see, this was transformed by a Q, which is this Q. I hope this is kind of straightforward. In the tutorial session, I will solve more questions and more examples for you to follow and understand what we are doing. I hope this helps understand the concept. So basically, you can represent this. The next class, the next lecture, I'll talk about doing the same transformation for a tensor. But what we've just done is we've taken a vector, right, and we've transformed it. We've transformed it by using a Q, right? Exactly. So the vector itself does not change, but its components change. Because if you find if you look at A, 2, 0, 0, if you say 2 squared plus 0 squared plus 0 squared and find the square root, you'll be getting the same. You're getting 2, sorry, not 4. That's, you're getting 2, right? If you do that for A prime, you still get 0 squared minus 2 squared plus 0 squared. A prime will still give you 2. You see, both A and this have the same length, or length of the on its magnitude. They are the same. It doesn't change, but the components have changed, and the components have changed with respect to the basis with which it was defined. One was defined with E sub I, the one was defined with E sub I prime. I hope this helps a lot. I'll explain more. I'll explain for what happens and transformations for a tensor in the next video, and I'll give more explanation in the tutorial session. Thanks a lot.